Hello, my name is Tim-Lukas and I'm with Leibniz University, Hannover in Germany. Today I want to talk about loop detection and present our open source ROS package CMR LiDAR loop, which helps autonomous mobile robots to answer the following important question. Have I been here before? But first of all, why is loop detection so important? During SLAM, wheel odometry data is fused with other sensors, such as, for example, inertial measurement units for pose estimation of the robot. However, due to inaccuracies, a so-called odometry drift occurs, which means that as the travel time increases, the difference between the estimated position and the ground truth increases as well. Only if loops are detected and thus the robot recognizes that it is at a position already visited, this drift can be corrected. Thus, robot place recognition is essential for the long-term autonomy of mobile robots. For this purpose, visual methods are widely used and are stable for static environments. However, the reality is dynamic. Objects move, seasons influence the appearance of the surroundings, and, depending on the lighting, images of the same scene differ. In these situations, visual methods are often not stable, are often not robust. For example, the illumination change can already lead to failure within a few hours, and places already visited cannot be recognized by the robot. Instead, actively illuminated sensors such as LiDAR scanners are robust in such situations as generated point clouds are illumination invariant. Although methods for LiDAR-based loop detection are found in the state-of-the-art, they often do not include the important scan registration and verification techniques to reject false positives. Our work presents a modular open source ROS package that can be used to extend visual SLAM methods with LiDAR-based loop detection and also includes the important steps of registration and verification. The basis for this is the widespread online SLAM library RTAB-Map. It is suitable for large-scale and long-term online SLAM in changing environments due to the use of the different memories. Although LiDAR data can be used by the proximity detection module for loop detection, the data is only marginally used. First, the use 2D ICP algorithm is a simplified method for loop detection. Second, this module only searches within a constant radius for loops, which is problematic due to odometry drift. And third, a local search is useless at the beginning of multi-session operation because the position in the old map is unknown. To counter these problems, we have developed CMR LiDAR loop. The main steps consist of a loop search, the registration of the corresponding point clouds, and a detailed verification with different criteria. Typically, a scan consists of tens of thousands of points. It is a large amount of data whose dimension must be reduced to realize efficient loop search. For this purpose, we use scan descriptors which are computed within a few milliseconds and represent the point cloud with different geometric features. Features of type 1 map the point cloud to a real number, for example, simple quantities such as the mean range, and features of type 2 are range histograms with different container sizes. With our chosen parameters, we were able to describe the high-dimensional scan with 843 real numbers. To predict whether two point clouds come from the same location, our extension uses a trained ADABUS classifier. Now, if you store the scan descriptor for each node, you can search for loops between the current node and map nodes based on these features. As already explained, a large loop, a large odometry drift is present. the loop search carried out in a constant radius is problematic, because the estimated position is highly inaccurate and loops are searched for in the wrong map area. Accordingly, we follow a different philosophy, the use of a variable search space depending on the position inaccuracy. The search radius consists of two parts. In the constant radius Rmin, loops are searched for if the current position can be assumed to be without errors. In all other cases, the estimated position is subject to error, which is taken into account by the second component. Thereby, Gmax is the length of the longest major axis of the 95% confidence ellipse of the two-dimensional position. For this purpose, the odometry data is processed by the extension. In case of a detection, the scan registration is necessary to close this loop. Registering raw point clouds is computationally expensive, and regions can also and scans can also contain regions that prevent successful registration. Examples are points on the ground or regions generated by reflection of the laser beam on glass fronts. To counter this, several filters such as voxel grid filter or intensity filter are executed consecutively. The pre-processed scans can have a large translational and rotational offset. Using a local method like ICP would not be expedient due to a convergence into a local optimum. Consequently, a rough registration with fast point feature histograms takes place first. Because of a partial overlap, not every key point has a match, and a large number of incorrect correspondences would be possible. These outliers negatively influence the registration, and therefore we use an outlier rejection scheme based on RANSAC. With the filtered correspondences, the initial alignment can be completed using SVD. The transformation of this global method is the initial guess of ICP, and this local method can then be used to further refine the registration. Since adding a wrong loop has catastrophic consequences for the SLAM system, our paper presents several loop verification criteria. These are based, for example, on the map positions of the individual nodes or on the number of inliers during initial alignment. If all criteria are met, the loop can be added by a link in RTAB-Map, and the graph can be optimized, and the odometry drift can be corrected. We have performed 3 different validations. The first experiment was used to train the loop detector and to tune precision recall. Training data with 1248 nodes were recorded on our campus, and as the distance at which the detector should treat a loop pair as positive, we choose 3 meters. With this distinction, the set is divided into about 11,000 positive pairs and about 800,000 negative pairs. We trained 50 detectors with different training data and compared them on an independent test data set. All detectors were compared at an error rate less than 1%, and the best detector detected 47% loops correctly and only 0.8% incorrectly. Due to our loop verifications, this error rate is acceptable, and we perform the further experiments with this detector. The presented method is furthermore validated in an experiment under challenging conditions. Since the introduced extension shall support the loop detection, we compare RTAB-Map extended with our work against the default operation. Thereby, the classical task of a mobile robot is considered. Map the environment and extend the map on another day at a different time. To do this, we first mapped our university campus and investigated whether our robot could locate itself on the map at a different time. 5 paths were driven, which are shown in blue on the map. Due to the dynamic environment, RTAB-Map did not detect any loops and therefore a localization for all of the 5 paths failed. In contrast with our method, a localization in the map of the old session was possible in 4 out of 5 paths and the mapping could be continued. Loops were detected in the 3rd path, but localization failed due to a wrong transformation matrix. Similar experiments were conducted in 2 challenging indoor environments, an entrance hall with many glass fronts and an office environment with several corridors. RTAB-Map operation realizes successful localization in 2 out of 6 paths, whereby in the respective areas a change in sunlight has a small influence due to a large amount of artificial light. Using CMA LiDAR loop, a successful localization is present in all 6 cases. Combining the results of the indoor and outdoor validation, RTAB-Map realizes a successful localization in 2 out of 11 cases, and in contrast to that, with a proposed LiDAR extension, it was possible to localize in 10 out of 11 paths. In the 3rd experiment with a car in traffic, we show the general applicability of our approach in the paper. We use the widespread Kitty benchmark and the results are comparable to the state-of-the-art LiDAR method LOAM. You can find our ROS package and detailed documentation at the links shown. Thank you for your attention.